Even in ancient time, men were wondering about the existence of the features of the Earth's surface, such as plains, mountains, volcanoes, and the like. During those times, they witnessed how lava and ashes came out of volcanoes, they felt the trembling effects of earthquakes, and they saw the evidence that land areas had risen above the water and sunk beneath it. Men tried to explain these phenomena as best as they can. Unfortunately, these occurrences were not interpreted correctly because the vastness of geologic times was not appreciated. Until such time in the 18th century, the modern approach to geology was clearly expressed by James Hutton, a Scottish geologist. Known as the founder of modern geology, he logically concluded that the Earth's history could be interpreted by tracing it backwards, from the present to past. He explained his theory called the principle of uniformity, also called uniformitarianism. This principle is often represented by a statement that the present is the key to the past. Elaborately, this means that the same geologic processes that is changing the rocks today are the very same processes that changed them in the ancient time. Since then, working on the basis, geologists have formed theories concerning the development of the landforms found all over the world. Most of the theories are generally accepted as fact. However, we should remember that geologists differ in their interpretations of individual observations. All the movement of the solid parts of the Earth are included in the term diastrophism. Diastrophism, or the large scale of the parts of the Earth's crust, is the process of deformation that changes the Earth's surface. It produces many of the basic structures on the Earth's surface such as plains, plateaus, and mountains. The movement of molten rocks beneath the Earth is responsible for the formation of volcanoes. Volcanism produces changes caused by the forces arising within the Earth's crust. Earthquakes are the result of the sudden release of energy that comes from stress on rock beneath the Earth's surface. Diastrophism, volcanism, and earthquakes are closely related. All are involved with the shapes, arrangements, and interrelationships of the different parts of the Earth's crust and the forces that change it. Thus, many of the features describing diastrophism can also be found associated with earthquakes and volcanic features.
The major forms of diastrophism are associated with either faulting or folding. Layered rock can fold in several basic ways, as a response to compressional stress. There are three types of fold: anticline, syncline, and monocline. The layers of rock in an anticline resemble an arch, or upside-down letter V layers in a syncline from a letter V, or U, resembling through. The two sides of an anticline or syncline are called limbs. A monocline only has one limb, resembling half of an anticline. 2 further describes folds. Geologists define axial plane as imaginary surface that divides a fold as symmetrically as possible, one limb on each side. The line made by the lengthwise intersection of the axial plane with beds in the fold is termed the fold axis. If the fold axis is not horizontal, the fold plunges. The angle between the line of the fold and the horizontal is the plunge. Folds in which the limbs have near equal dips are called open or symmetrical. As the amount of shortening increases, the limbs of fold will rotate, so will the axial plane. The resulting folds are called asymmetric when the limbs on the either side of axial plane have different dips. With further shortening, both limbs may dip in the same direction. Folds that have reached this stage are overturned. At the limit, both limbs become nearly horizontal, one right side up, one inverted, resulting in a recumbent fold. When folding is pronounced, and on a large scale, regional mountain, building, or orogeny results. Fold mountains are actually formed by the crustal uplift and folding produced by compressional forces. It occurs along convergent plate boundaries, between two continental plates, or between an oceanic and a continental plate. Rock strata get bent and crumpled, and massive layers of the crust are uplifted. As a result, the Rockies of western North America is a good example of a major range of relatively young fold mountains. In eastern North America, the Appalachians are ranges of old fold mountains. The Himalayas in Asia and the Andes in South America are other good examples of young fold mountains.
These giant gashes in the Earth are reminders of our planet's awesome power. They are fault lines, fractures in the Earth's crust where huge slabs of rock slowly grind past each other. Most faults we can't see, but here in California the San Andreas Fault is visible at the surface.
You can't have an earthquake without a fault. And I'm standing right now on what is perhaps the most famous fault in the world, the San Andreas Fault, that extends from Mexico down south, way up to Oregon in the north. This is one of the few places in the world where you can stand with 1 foot on one tectonic plate and one on another. In other words, this ground here is attached to New York and Iceland. The ground here is attached to Hawaii and Japan.
The San Andreas Fault sits on the boundary between the North American and Pacific plates. It's called a strike-slip fault, a place where two plates collide and try to slip past each other. As these plates move or creep in different directions, sometimes they get stuck. The longer they stay stuck, the more tension builds and the bigger the eventual quake. In other places, the plates move smoothly past each other. These areas buckle as the Earth shifts. The changes are subtle. Roger Bilham keeps track of these changes with his creep meter, a device that measures movement along the fault. A computer collects data every minute for a year. This jump in the graph tells him the Earth shifted about 5 millimeters in a couple of hours. A small shift like this can have huge consequences for us.
That might not seem much, 5 millimeters, but it's affecting a long section of the fault, maybe 5 miles long, involving millions of tons of rock. Now, it really doesn't matter here. This is a nice sort of field, there aren't any people, but further north, this creep process and the things that are happening beneath the Earth are far more sinister.
The San Andreas Fault and its branches trigger more than 10,000 quakes a year. Sometimes the results are devastating. Just ask the people of Los Angeles or San Francisco. Over the last 2 decades, major quakes rocked both of these cities. Life goes on, but the risk remains. In an area this active, the next violent tremor could happen at any time.
A fault is a fracture in the Earth's crust, along which 2 blocks of the crust have slipped with respect to each other. Faults are divided into 3 main groups, depending how they move. Normal faults. Normal faults occur in response to pulling or tension. The overlying block moves down the dip of the plane. Thrust faults. Thrust or reverse faults occur in response to squeezing or compression. The overlying block moves up the dip of the fault plane. Strike-slip. Streaky-slip or lateral faults occur in response to either type of stress. The blocks move